and do it again.
Oh, awesome.
So yeah,
are you
that really helps.
going back to the YouTube ones or the ones we do in class?
The YouTube one.
Oh, good.
Because then it's quieter and it's just you, so I can.
Yeah,
know,
and I kind of just get to the point,
Yeah,
like, I just
and
go
it's-
pom, 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 pom.
Oh
Yeah,
my
so-
gosh, that's so helpful.
Awesome, good, I'm glad, I'm super glad.
Because I'm gonna go back to the one where you have to do conversions, because some of those conversions, they're a little confusing, so I want to go back and go over them again on my own, but at least I know they're there, so I can.
Mhm.
So
And
that's-
they're pretty short, because I just get right to the point.
Yeah,
I have to make 1-7 yet, I'm gonna do that tomorrow, and then all of unit 1 will be done, and then I'm gonna make, I'm gonna try to get 2-1 done before I go, but we're not gonna do 2-1 until I get back anyway, but in case
Yeah.
anybody wants to get started. I'm gonna get those going, so.
but that helps so much when you have a question you want to ask more on, you can always go back, because I think you just doing it is so much, it's to, like you said, short and to the point.
Awesome.
It's like we have a very small attentive class tonight.
So we're just gonna get to business. So page 91.
Thank you.
I'm gonna share my screen. Oh, there we go. We don't necessarily have to read through all of this, but it talks about how if you go to debt.org, it's a website, and it says the average household in the US has a little over $103,000 in debt. And then here is the federal government's total debt. Isn't it crazy? It's not hundreds, thousands, millions, billions. It's 22 trillion.
Wow.
Yeah, it's crazy. So we're going to talk about scientific notation today. Really, really big numbers and trying to making them look a little bit more realistic. And then really, really small numbers, the same thing. So maybe like this is the size of our government debt, which is very, very, very large. And then we have like the size of a virus, right? Like the coronavirus, which is very, 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 very small. So sometimes we have a need to use scientific notation for both types of numbers. So it says if you track the national debt over the last 90 years or so, you'd see that its growth, while alarming, follows a fairly consistent pattern. On average, the debt has grown by about almost 8% per year. If that trend continues by 2050, it will be this. 276 trillion. And by 2100, it'll be this, which is thousands, millions, trillions, billions. No, thousands, millions, trillions, quadrillion, 12 quadrillion. I've never even used that word really. So it says if you're like most people, you have no idea what those numbers are actually mean. They're just too big to get any perspective on them other than, wow, they're really big. So to make it easier and work with numbers of ludicrous size, we'll use a clever method for writing them using exponents. So powers of 10. So these are all positive powers of 10, multiplying by a value of 10, 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th. And in your, in Desmos, if you're going to write something in a power, you're going to use your shift key and your 6, because above your 6 key, it's that this symbol right here is called the caret, and that will make it go into an exponent. So for all those at home, we're going to use Desmos quite a bit today.
Okay.
So, and because these are all bigger than 10 numbers, the exponents are positive. Okay, so we would write 5 billion as this, 5 times 10 to the 9th. So it says, now let's take a look at some debt numbers. In 1930, the national debt was about 16 billion, which is right here, 1.6 times 10 to the 10. And then by 1995, it had grown to about 1.823 trillion. And I think we said we're at 27 trillion, 22 trillion. And that's, I'm sure it's way bigger than that, because this was printed a year ago, and all those things, all the money we printed in the last few months with all the coronavirus bills,
Yeah.
it's out of control. It's getting past the point of return, actually, which is frightening in itself. So because the first part of a number in proper scientific notation is always a number between 0 and 10, you can easily compare the sizes of numbers by looking at the size of the exponent. So the second exponent, 12, is 2 bigger than the first exponent, 10. So does everybody see that, 10 and 12? And because these two numbers, 1.6 and 1.8, are relatively the same,
Yeah.
they're kind of like a 1-to-1 ratio, then we can just look at this power of 10. So it's 2 bigger, so that would be 10 squared, or 100 times.
Okay, 10 times.
That's kind of a quick way.
Mhm.
So it says Earth is about 2.57 times 10 to the 7th miles from Venus, and about 4.67 times 10 to the 9 miles from Pluto. About how many times further away is Pluto? So whenever we say how many times something is, what math action will we do to figure that out?
How many times further?
Mhm.
Divide,
Do what?
divide.
Divide? Yep, that's what I would do.
Mhm.
And so we can do some estimating. 4.67 is about 2 times bigger than 2.57. Not quite, right? We can do, we'll do a little estimate, and then we'll go to Desmos. So this is about 2, approximately 2 times bigger. And then we can see that on the powers of 10, 9 is 2 times bigger than 7.
Mhm.
So I'd say approximately 200 times bigger. But like I said, we can go to Desmos to check it out. Let's see here. Also, Darla, I know you came after, I think maybe I mentioned this, but tonight I'd really like to get through 1.6 and 1.7. So I'm kind of directing everything, if that's okay, because that way you at least have all the stuff to guide you next week while I'm gone to get working together. So thanks.
Not a problem.
Thanks all for being flexible with that.
I just came from a massage, so I'm flexible no matter what.
Oh, I like it.
Lucky girl.
My massage lady beats me up. I never leave there thinking I feel like I just had like a relaxing massage, but I need it. I have a bad back, but it never feels like just where I want to fall asleep. It's like, oh, I didn't think I was even hurting there until you touched me. Okay.
Yeah.
So 4.67 divided by, so this is going to be a fraction. Anytime there's a fraction, I kind of just start the fraction and then I edit it like it needs to be. So this is times 10 to the 9. And then that's times 10 to the 7. How were the school pictures, Darla? Oh, you're muted.
The wrong way. They weren't really good yesterday. Today was pajama day.
Oh, what grade are you this year?
I'm in second.
So are you a
Parapro?
Yes, I'm a parapro.
Parapro.
Yes, love the little deers.
Oh gosh.
I have a granddaughter in 3rd grade. Mhm.
Ah,
And a grandson in 7th grade.
very cool. So we estimated about 200 times bigger, and it came out to be exactly 181. So we were pretty close.
Yeah. Now, would you have to do any rounding or just leave it at 181?
No, because it says about, so
Okay.
we're kind of estimating. So
Okay.
it's really about 181 times. So writing large numbers in scientific notation, we're taking where the natural decimal is, which is to the right of any zero, any your very far right number is not necessarily 0. but then picking it up and moving it so there's just a single digit to the left of the decimal. So this one, we would pick it up and move it to the, just to the right of 3. And then we have to count how many places we had to move it. So we moved it 3 zeros and then the 8, 6, and 9. So a total of 6 spaces is how far we moved it. So we have to tell how many powers of 10 did we move. So number 2, I'm gonna let you ladies try 2 and 3. And then I'll check in with you. I'm gonna mute myself while you do it.
Okay, so. Am I on? Okay. I'm on.
Everybody get those 2 problems, 2 and 3?
Yeah, I think so.
Anybody want to share what you get?
Well, if you have to move the decimal 1 to the right, correct?
Well, our decimal's right here, right now, right?
Okay, so you have to move it times 1, 2, 3, 4, 5, 6, 7. I'm trying to understand how I explain myself. If it's decimal point to the end of the whole number, so you move it to the left, so it's just 1 digit before it.
Yeah,
So you do what, 3, and then the point,
yeah,
and then all the numbers after it.
yeah. And then if there's trailing zeros here, we don't have to, but we'll put them there for now so we can see exactly what we did.
Okay, so then you count the digits at, and it's 10 times however many digits are after the 3.
Mhm. Yeah, how many places we moved the decimal?
Right, right.
Yeah.
1, yes, 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, and it's a positive 8.
Okay, so when you said you're just gonna put the zeros in there for now, why wouldn't you?
Well, if you saw it on the calculator, they probably wouldn't have the zeros.
Oh,
I'm
okay,
just saying, I'm doing it so that you all can see the place values.
okay, okay.
Yeah. So then what would it look like for number 3? Sorry, I've got wax or something in my ear, and I went to the doctor today, but now there's just water in my ear. So
Boy.
Anybody have an idea for number 3? Oh, was there something up there?
So I have a question.
Sure.
So for number 3, 238,900. So you would assume that the decimal is all the way to the right of the number, correct?
Yep, if it's a whole number, we assume it starts right there.
Okay, so then and for it to be in the powers of the scientific notation, you have to go all the way, move it all the way to the left and leave it 1 digit, like 2 point,
Yep,
right?
excellent. And Melissa put it in the chat to everyone. She had it. Good job. So yes, Teresa, we're going to move it there, just so there's a decimal to the right of the 2. And then we moved it 5 places.
So we 10 to 5, right? Okay.
Yep. Good job.
Okay.
I'm going to keep that chat up. So can you guys see my chat that I have open or no?
No.
Okay, I just wasn't sure if it showed on my, but it doesn't show on my screen because I'm not sharing that. So
I do see it if I click on it.
you've got yours. Okay, good. So let's just keep that up because I think that's the best way for Melissa to communicate with us.
George, I left my water out there. Can you bring it for me?
So the next page says we can also use scientific notation to write very small numbers. So numbers that are between 0 and 1. Okay, so between 0 and 1. So very small numbers. They're not negative, but they're just really, really small. They're going to be listed like this. So 1 divided by 10 or 1/10 is going to be a 10 to the negative 1. So we're going to use negative exponents to indicate that it's between 0 and 1. And then if it's 1/100th, it's kind of a negative 2. So, and then if you look, when they're in the denominator, the powers are positive. But when we write them in the numerator, they're negative. So we have to show that negative tells us that it's a small, small number. A positive means a really big number. So right here, if we take a number that is between 0 and 1, so 0.000437, and we write that in scientific notation, again, we're going to pick up the decimal. We're going to place it to the right of the first single digit, 4.37, and then we have to write how many powers of 10 did we move. Well, this time we moved 4 places to the right, and so we have to write it as a negative. So when you're moving from decimal notation to scientific, if you move the decimal to the right, your exponent is going to be negative. So really small numbers have negative exponents. So let's do this first one together. A typical flu virus measures between this number and this number. They're very small. So I'll do the first one and then I'm going to let you all work on 4, 5, and 6. So we're going to pick up the decimal and I'm going to place it to the right of the 8. So I'm just going to make that 8.0 just to show where the decimal is.
Because that's the first non-zero number. Is that why?
Yep, good job. The very first non-zero digit. And then I have to count how many places I moved it. So I moved it 3, 6, 7, 8. So I moved it 8 spaces, and because it was a very small number and I moved it 8 spaces to the right, I have to make it a negative exponent. So let you all try the next one. Did anybody get the the other ones? The other one for 4 and then 5? Want to share?
Is it 12 point times 10 negative 7?
So 12 is close, but we have to put the decimal so there's only a single digit to the left of the decimal.
Okay, I didn't hear that part. So it would be 1.2
There you go, times 10.
and to the negative 7.
Yep, still negative 7. Yep.
And is that because it says, move the decimal to the first non-zero digit? So it'd be
Yep.
right after the 1.
Yep. There can only be a 1 through 9 to the left of the decimal.
Okay.
Yep.
And then E. coli is 7 point times 10 negative 6 to the power. Yeah.
I would agree with that too. Excellent. So then 6 is asking another one of those, which is bigger. So it says,
I want to say E. coli.
you want to say the E. coli?
Yeah.
How did you check it?
It's the lowest number. I
Oh,
did-
so it's the E. coli. Well, this looks like it's the lowest number, but negative 6 is actually closer to 0 than a negative 8.
Oh,
Because if you think about this one is closer to the number 0 than this one is, right?
Oh,
It's
yeah.
got more.
I get it.
Yeah.
it just looked a
So-
smaller number.
Yep. So the smaller of the virus is actually going to be smaller. So the small flu virus is going to be small, or which is bigger. I'm sorry, it said which is bigger. You are right, Darla.
Okay.
I don't know why in my head I was
Is
thinking
it
which is
to
smaller.
me, it just means the opposite.
Yes, So which is bigger? This one's bigger because it's closer to 0.
Yeah,
It's not as small. Sorry about that.
that's
I've done
okay.
this 3 times in the last 2 days. You'd think that my brain would still be working at 6 o'clock at night.
No.
No excuses. So yes, the E. coli is a little bit bigger, but we want to know how many times bigger. So we're going to put the bigger one on top.
Oh, okay. So now we got to do that part.
Yeah, and we're going to divide it out. So we're going to do the 7 times 10 to the negative 6 over 8 times 10 to the negative 8. And we can estimate this because 7 and 8 are relatively close, right? So they're gonna, we can kind of actually do this without decimals because they're gonna be about a 1 when you take 7 divided by 8. So we can kind of
Right.
leave it at that. But what we need to look at are the exponents. So a negative 6 subtracting a negative 8, because we want to find the difference between them. And then negative 6, that becomes plus 8 because when you're adding an opposite. And so this becomes a negative 6 plus 8 is actually a positive 2. So it's 10 squared bigger, or approximately 100 times.
And that's because the negative and the negative make a positive,
Yeah,
correct?
this negative and this negative make a positive. Yeah,
Yeah.
we were trying to find the difference in their exponents. And most, some people can just look at it and go, oh, there's just 2 different. And that's fine too. I was just kind of showing mathematically how that works. So it's about 100 times bigger. So let's look at 7 and 8. We're going to go in the opposite direction. Now they're giving us the scientific notation, and we have to move to decimal notation. So the sign of our exponent tells us exactly what way we're going to move our decimal, because if we go up here to the example, the example says 4.01 times 10 to the 8. The 8 is a positive, so we're moving the decimal in a positive direction on the number line. And the second one, 3.2 times 10 to the negative 5. The 5 is a negative, and so we're going to move the decimal in a negative direction on the number line. So number 7 on the red blood cells, are we going to move the decimal to the right or to the left?
To the positive
right.
is to the right, correct? Positive is to the right.
Yep, so positive to the right. So 5, and then we're going to move it around the 4 once, and then we have to add 5 additional zeros.
Yes, that's what I got.
I'm going to give a hint. Everybody circle this one.
Okay.
And we're circling this 7A because this is the answer to your lesson check.
Okay, but I have a question.
Sure.
You have the 5.4, and if you're moving it, you're saying 6 to the right, so you count 4 as one of the digits that you're moving. So that's why you had a 4 and then 5 zeros. right?
Yep.
Okay.
So I moved 6 places.
Okay, so it
One
doesn't.
of them was going around the 4, and then the other
Okay.
5 were zeros.
Okay. Okay.
You got it. And then what about the next one? Oops.
Okay, so we have to move that one. 1,
The opposite way.
2, 3, 5, 6, 7, 8, 9. So 1, 2.
Oh, Melissa's got him in the chat. Let's see what she. I'm not trying.
Yep,
to do it
That's
in
what I got, Melissa.
Oh, see. I agree with that too. So it's
8
a
zeros.
so 8 zeros.
Yep. You can eat what side? Okay, I'll be right back. I gotta put them out.
Sounds good. Good job, good job.
Okay, and that's because you moved it from the 3.6, so the 3 counted as one of the digits that make up the 9.
There you go.
I wish I got everything else this easy.
That's okay.
Hmm.
You're going back to school. It's been a while. Part of it is just kind of getting back in the swing, you know what I mean? So you're just kind of training your brain to grow, and it's gonna start moving quicker. Like, don't worry, you're getting there.
But
So
I'm kind of reviewing, it's nice that you have those lessons taped so I can go back on a couple of the ones that I'm not so quite sure how to do. So that'll be nice. I can do that.
Yep. So number 8 says, when a number written in scientific notation has a positive exponent of 10, what can we say for sure about the number? What do we know for sure?
Positive exponent on 10, so bigger than 10,
Mm-hmm.
number is bigger than 10, or it wouldn't have an exponent, correct?
Right, so it's at least 10. If a number between 0 and 1 is written in scientific notation, what can we say for sure about the exponent on 10?
Zero and 1. There would be an exponent on 10, right? Or is it-
If it's a number between 0 and 1, like this number up here,
okay,
that's a number between 0 and 1.
It's a
Oh.
negative exponent.
negative then. Right.
Okay.
Is that right? It'd be a negative exponent?
Mm-hmm. Excellent. And number 10 says, fill in the blanks. If a number in scientific notation has a negative exponent on 10, to convert to decimal form, move the decimal place
To the left.
left because the number is
Less than 1 or smaller or whatever.
Mm-hmm.
What's better, smaller or less than 1? Or does it matter?
or we could say between 0 and 1.
Okay.
There we go. Awesome, awesome. Now, another way that we're going to see scientific notation, excuse me, in some calculators, you're going to see it written like this with an E. And an E, the only difference is an E is just representing the times 10. So for instance, this one right here, this is the same as 1.2375 times 10. That's just the E. And then the 4 is the exponent. So the E is just another way of saying times 10.
Okay, so E is for exponent.
Yeah. And so 11 says, write the result of the calculation. So the answer right here in scientific and decimal notation. So this is going to be 7.44 times 10 to the third. And then what would it look like in decimal notation? I gotta keep paying attention
Oops.
to Melissa's thing here.
Move the decimal 3 places to the right from the 7, because it's positive, correct? So it'd be
I agree.
7440, correct?
You had 7440.
Yeah.
You're moving it three places to the right.
Great job. You got it.
Yeah, just remember that on my test. It seems easy here because we're doing it with you.
Okay, so let's go ahead and flip the page. So the next page, so page 96 here. It kind of just goes through with us the words, because a lot of time big numbers are written with words.
I'm like, but I found it.
Like when the Publishers Clearinghouse, when they're going to write me a check, it's going to say millions on there. State of Michigan writes me a check, right, for when I win the lotto. Okay, so 100 is 10 squared, thousands are 10 cubed, and then in between thousands and millions, you have 1,000s, 10,000s, and 100,000s, right? So
Okay.
those are going to be powers of 3, 4, and 5. And then when you get to 6, you're in the millions. They're called like they're called decades, like not decades, but they're called periods. So there's the 1,000 period, the millions period, the billions, and the trillions. So that's why they go by 3, 6, 9, and 12 right here. Because once you get to the period, then you've got the ones, the tens, the hundreds, and then it goes to the next period of ones, tens, hundreds.
Oh, okay.
So I'll walk you through it. I just wanted you to see the pattern. So this says the size of the national debt in dollars for selected years from 1930 to 2019 is shown in the table and the graph. In the third column of the table, write how the debt would be read aloud. I just have to ask, am I sounding really loud? Because I can't hear it all out of this ear.
I think it's fine.
I'm not sounding extra loud tonight. Okay.
Not to me.
Okay. So 1930, the debt in dollars was 1.6 times 10 to the 10th. And that is reading 16 billion. Okay, because the 9th would be just single billions, and this is the 10 billions because it's 10.
Okay, say that again. I didn't quite get that one.
Okay. So because this is to the 10th, we're in the 10 billions, where the 9th is just a single billion.
Oh, I got you.
So
Okay.
what you can do is you could, if you want to be able to read it correctly, see how this 1.6, you could
Mhm.
just move the decimal over one, so it says 16, and then
Mhm.
you just have to lower your exponent to 9, and then you know it's the billions.
Got you. Okay.
So the next one's going to be 51 billion. And then the next one is going to be 257 billion. We're really ramping up the spending here. Then 286 billion.
And you're saying billion because it's the billion is at the 9, the trillion is at the 12, and it says the 11, so it's the billion, correct?
Yeah, so billions are really the 9s, 10s, and 11s. The
Okay.
singles, the 10s, the 100 billions. So we're in the 100 billions.
Okay.
And then 371 billion. And then last but not least is the 908 billion. And now the rest are going to be in the trillions. So 1990 is 3 trillion because it's the 12. And then the 233 is billions. So this one is 3 trillion.
Oh my goodness.
233 billion. Isn't this crazy?
Ooh-wee.
Then 5 trillion. 674 billion. And now the exponent went up one, so it's 13 trillion in 2010. 562 billion. It almost tripled in that 10 years, 2000 to 2010. Isn't it crazy? And now look at 2019, it's 22 trillion 618 billion.
Now, could you do that on decimals? Yeah,
Let's see, because there's so many zeros.
I just wonder how.
Decimals might just put it back in decimal location. I think it has a limit of how many zeros it will go, but let's try it. It won't put it in words.
Right. Oh, okay.
What am I doing here? But it will put it, it might put it in zeros, like, so let's just try. Let's do 2.2618. Is that what that last one is?
2.2618. Yeah.
10 to the 13. Yeah, see, it just writes it.
Oh, I see.
But you could check and see if it comes out to be the same. If you typed in what you think it is, 22618 would be 1, 2, 3, 4. And then you got 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros and hit enter. Oh, well, that didn't do anything, did it? I thought maybe it would put it in scientific notation. Let's see if in the down, if you hit the keyboard, there's some menus. So you can go to the functions menu and let's see if it's not in the stats. It's not in the distribution. Miscellaneous. I don't see anything there that would. Yeah.
No.
No. Won't.
What's the thought? I just wonder, it does seems like it does everything else.
Yeah. Well, we're going to use it a ton in 1.7 today. It's
I'm
going to
sorry?
be. It's going to
Oh,
be.
1.7. Okay.
Yeah, less than 1.7. Okay, so you can see this crazy growth in our expenditures right here in the graph. So it starts at 0 like a good graph should, and it's very, very low because up here, because the scaling has to be so big because in the last 20 years, it's jumped up this much.
Wow.
It's crazy. So number 13 says the population of the US was roughly 1.23 times 10 to the 8th, so in the billions in 1930, and 3.3 times 10 to the 8th in 2019. This is the population. If the national debt were to be paid off by dividing the total amount owed evenly among all citizens, how much would each have owed in 1930, and what about in 2019? So let's look at 1930. So if we want to find out how much each person would have to owe, what numbers do we need? So we're looking for money, right, per person. That kind of helps us set it up. So when we say money, we're talking about debt, right?
Mhm.
So we have to use the debt from the table for 1930.
16 billion.
Yep. So I'm going to use the 1.6 times 10 to the 10 because we're going to have to put this in the decimals. 1.6 times 10 to the 10. All divided by the number of people in 1930. So 1.23 times 10 to the 8.
Where'd you find that number?
Right here.
Oh, okay.
Yeah.
Oh, the population was roughly, okay.
Yep.
Yeah.
And then,
How easy
Wait.
is kind of overlook that stuff.
yeah, and then I'm gonna lay this out for 2019, and then we'll just go and do them both in decimals. So in 2019, the debt is ginormous, 2.2618 times 10 to the 13. over the population, which was 3.3 times 10 to the 8. So I'll let you all go to Desmos and work on that, and then we'll share here in just a minute.